Let's go through the solution for Chapter 7 practice problems number 2. Prove the following using mathematical induction. 1 plus 3 plus 5 plus ... In other words, we're going to continue going 7, 9, 11 until we get to 2n minus 1 is going to equal n squared for all integers where n is greater than or equal to 1. Now there are two steps that you need to go through. If you're missing either of these steps when you do a problem like this, you're going to lose points. So make sure that you do both of these steps. We have the basis step and we have the inductive step. So in induction, you basically want to show that this works one time, and then you're going to prove, kind of like a domino, that you do for one value, you figure this out and prove it for one value, and then you want to show that it also works for the next value. So like if it works for 1, then it works for 2, then 3, and there's kind of like a domino that gets knocked over. So let me show you how that works. Again, the first thing you're going to do is find a value for n and plug it into this problem and show that it works. So if I let n equal 1, since n is the smallest number, and that's usually what you do, is you find the smallest number. 2 times 1, replacing n with 1, minus 1 is going to equal 1, since that's 2 minus 1, or 1. And then you square the 1 on the other side of the equation, and it's going to equal 1. So we've shown that this works in one instance. Now we move to the inductive step. And this is where students often kind of trip up, so be careful here. We're showing for all integers where k is greater than or equal to 1, if p of n is true for n equals k, then it is true for n equals k plus 1. Okay, so what we're going to do is we're going to take this whole equation and replace all of the n's with k. So 1 plus 3 plus 5 plus ... plus 2k minus 1 is equal to k squared. Okay, then what we're going to do is we're going to replace n with k plus 1. So we're going to take this whole equation and replace everything with k plus 1. So it's 1 plus 3 plus 5 plus, we had 2k minus 1. Now we replace the k with k plus 1. Okay, and on the other side of the equation we had n squared. Now we're going to replace that with k plus 1. Okay, so from this equation, if you look closely at the first part of this, we have this ellipsis, and that is a little bit clunky. So the first part of this, we've shown that that whole mess of an expression is equal to k squared. So I can take this whole expression and replace it with k squared. Okay, again, I'm taking this and replacing it with k squared by substitution. Then whatever is left on the left-hand side of the equation, this 2 times k plus 1 minus 1, I'm going to replace that and put that down here, and then minus 1. Now I can simplify this using algebra. I have 2 times k plus 1, which would be 2k plus 2, minus 1. Then I simplify this, and you can see that it's k squared plus 2k, and 2 minus 1 is 1. Okay. Now I can take this expression. If you remember in algebra, we can factor. This is going to be k plus 1 times k plus 1, or k plus 1 squared. Magically, as in all of these problems, the left-hand side of this equation and the right-hand side of the equation need to equal each other to prove that it's true. So we already had that expression k plus 1 on the right-hand side. Now we've proven the left-hand side has that same value. Since we've proven that both sides are equal, we were able to show the basis step work and the inductive step work. Therefore, we have proven that this is true.